Hello everyone, my name is Alberic and this is a joint work between the Automatic Control Laboratory at EPFL and the EPFL rocket team. We will present to you our work on guidance, navigation and control algorithm for sounding rockets using a small-scale electric rocket prototype. In the aerospace industry, test vehicles are usually close to full-scale and chemically propelled, making them complex to develop and operate. For example, the first prototype SpaceX built for the landing program was the Grasshopper vehicle, which was 32 meters high and had a maximum thrust of 540 kilonewton. We believe that a small-scale prototype that is closer in size and complexity to a drone can be a representative test vehicle while reducing the complexity of the project, thus making the research in this field more accessible. So we developed this test vehicle using standard drone components and cheap structural parts for a total cost of around $500. It is powered by two counter-rotating propellers mounted on a two-axis gimbal, so we have the same number of control as a quadcopter. The vehicle is 60 cm tall and weighs 1.7 kg, so we don't need any special authorization to fly it at low altitude in Switzerland. The control algorithm is a nonlinear model predictive controller. It uses the full dynamics model over a 2 seconds prediction horizon to track any target trajectory or set point. In this video, you see a simulation experiment to track a reference trajectory in green and a controller open loop trajectory in blue. Here is the same experiment on the real vehicle and using motion capture for accurate localization. The maximum tracking error in this experiment is around 10 cm, which we think could be improved with a faster control loop and a more precise test vehicle. In order to robustly track targets, an extended Kalman filter is used to estimate unknown forces such as aerodynamic effects or other kinds of disturbances. This scheme also enabled an estimation of unknown or varying parameters, such as misalignment of the center of mass or varying thrust due to ground effects. These perturbations are then included in the predictive model of the controller to achieve offset-free tracking. To evaluate the robustness of the controller when subjected to unknown perturbation, an experiment was carried out using a wind-shaped fan array to generate wind up to 5.6 meters per second. The extended Kalman filter is able to estimate the aerodynamic force and the controller compensates for it. While the control algorithm works well for short-term control, it has a limited prediction horizon length due to computational limitation. To track arbitrarily far away apogee or landing targets, we developed a guidance algorithm also based on model predictive control, but using a simplified point mass model and a reduced solving frequency of 20 Hz to generate long horizon, energy optimal trajectories, which are then tracked by the controller. In this video, we demonstrate how the guidance algorithm generates optimal trajectories to reach the apogee 3 meters high and then to reach the landing target 2 meters on the side. This video demonstrates the complete architecture being used with all GNC algorithm. As shown in this presentation, this simple and inexpensive testbed still allowed us to develop complex guidance, navigation, and control algorithms, and easily test them on representative conditions. As we rely on model-based algorithm, the experience we acquired on this first test vehicle can easily be used on the following scaled-up vehicles.